Our project title is Brain Tumor Segmentation of MRI Images Using Deep Learning Techniques. Our team number is 117 and the team members are Karthik Raul, Subodh Guzar and Kartiki Bhandakkar. These are the contents of our presentation.
Gliomas are the most common and aggressive type of brain tumor. MRI is widely used to assess these tumors. The goal of the project is to develop an accurate and efficient method for identifying and segmenting brain tumors in medical images using deep learning techniques. Project aims to address the challenges of manual segmenting brain tumors, which is time-consuming and error-prone task that can lead to inconsistencies and inaccuracies in diagnosis of the treatment. Also, by utilizing deep learning techniques, the project seeks to automate the process of brain tumor segmentation, providing doctors and medical professionals with a reliable and efficient tool for detecting and analyzing brain tumors. The project also aims to improve the accuracy of brain tumor segmentation, which can lead to more precise diagnosis, treatment planning, and patient outcomes.
For the project, the LGG segmentation dataset, which is a medical imaging dataset, was utilized. It contains MRI scans of patients with low-grade gliomas. The LGG segmentation dataset was created by the Brain Tumor Segmentation Challenge, which is a community-driven initiative. The dataset consists of MRI scans from 110 patients, with each scan containing 4 different image modalities. The masks were manually annotated by experienced neuroradiologists and provide a ground truth levels for use in training and evaluating segmentation models. Here you can see the distribution of the dataset. The number of positive samples are less than the number of negative samples, which is the case in most of medical datasets. This image displays the images which are present in the dataset. In the first row, you can observe the MRI scans of the various MRI scans of various patients, and in the second row, we can observe the masks which are present, which will be utilized for segmentation. As a baseline model, we utilized UNet. The UNet architecture is based on fully convolutional networks based architecture. Here is the architecture of the UNet model. The encoder part of the UNet model consists of a series of convolutional and pooling layers that reduce the spatial resolution of the input image while increasing the number of channels, resulting in a compressed representation. The decoder path consists of a series of convolutional and upsampling layers that increases the spatial resolution of the compressed representation while decreasing the number of channels. In addition, the UNet architecture also incorporates skip connections that connect the corresponding layers in encoder and decoder paths.
This is the performance of the baseline model UNet with Adam. The first graph shows the training and the validation loss over 50 epochs. The second graph shows the training and validation IOU over epochs. For our model, we modified the UNet architecture by changing the encoding layer to ResNex 50 backbone, and the corresponding decoding layer was designed. ResNex 50 is a variant of the ResNet architecture that uses a split transform mode strategy to increase the representational power of the network. This architecture uses ResNex 50 as the encoder, which allows the model to extract more powerful and discriminative features from the input image. The decoder part of the UNet is then used to upsample the features to the original resolution of the image. This is the overall architecture of our model. The model was trained using a combined loss function of cross entropy and dice loss with Adam as the optimizer. The following graphs demonstrate the performance of our model. As the number of epochs increases, we can see that the IOU score is also improving, indicating that the model is learning to better detect the masks in the MRI images. At the same time, the loss is decreasing, indicating that the model is learning to more accurately predict the mask. This shows that the model is trained correctly. Also, from the graphs we can see that the validation loss is also decreasing and not increasing as the epochs increase. This shows that the model did not overfit. This graph shows the comparison of all models we trained. We can observe that training IOU of baseline model was 0.5 and the validation IOU was 0.49. While our final model achieved an IOU of 0.79 on training and 0.75 IOU for validation. Here are the results for our prediction on the baseline model, and these are the results for our model. Here, the predicted masks are shown in red boundaries and the ground truth is shown in green boundaries.
The challenges faced during for this project, as UNet models have large number of parameters, it can lead to overfitting. Secondly is the variability in tumor appearance, as the size of the tumor and the shape of the tumor can be different. This can lead to a varying degree of heterogeneity present in the dataset. Lastly is the inter-observer variability, as interpretation of MRI images can be subjective. This can result in inter-observer variability, which can affect the reliability and consistency of segmentation results. These are the references for our project. And thank you for listening.